let's continue. So we have a data. This data is limited, as Dr. Chu said that it could be very costly, but we divide the data into F and V. And the T, in fact, T should not be in the possession of the authors. T is open-ended, all right? It's from the open-ended word, and very big. And author should have only F and V, fitting set and validation set. Then once we do training on fitting set, and we have like 20 networks, and we pick up the luckiest network from V based on the error on V. And the question that we were discussing, which is very, very important, and I really appreciate Dr. Chu's discussion with me, and raise super questions, and ask this kind of question many times. Whether the luckiest one on V, which was not trained on V, is training on F. Then you pick up the luckiest one or worst one on V, all right? And then what's the distribution of the luckiest one or the worst one or any other in between on T, right? And Dr. Chu said that, oh, my luckiest one maybe perform the best on T. And that was his question. That's he did not prove it, but that's really what he was asking, right? And my position was that if we understand the statistics, and I will give a diagram next on showing that in the absence of additional information, we cannot say that the luckiest one will doing better on the future T, or the worst one will do worse on the future T, or other way around. We don't. We don't. It's like we are drawing this is a huge dimensional space, right? The theta space is huge. We only pick up like say 60 million dimensional space. We pick up only 20 samples, and we are in not just the small sample problem in statistics. In statistics, they have a large sample problem and a small sample problem. Large sample problem typically look at the asymptotic behavior. Small sample problem, you have to look at the actual distribution, all right? Because the given example, they have to rank the statistics, whatever. Rank the statistics is for small sample problem. Our case is undersample problem, because the number of sample is much less than the dimension of the data. And so it's undersample problem, all right? If the number of sample is comparable with dimension a little bit larger, they call small sample problem. If the number of sample goes to infinity with a fixed dimensionality, then it's called large sample problem. Our sample is number of sample 20 is tremendously smaller than the dimensionality of the problem, which is 60 million, all right? So 20 sample out of 60 million, that's absurd.
Yeah.
It's undersample problem, all right?
I just want to maybe comment on that terminology a little bit.
Okay.
So typically we look at, in statistics, we look at the dimension of X, I should say. We look at the dimension of X, like, and compare this, I'll call it P, with N. So so typically, like, my expertise is mostly when P is fixed and N is large, so the large sample problem. And if P is growing with N, so it's like P is also large, but also N is large, then that typically we call it high dimensional problem. And we also look at asymptotics. It's just different asymptotics. And then you're talking about small n, and large. It's just that if n is very small, then we have to rely on, we call it a small sample problem. So there is still a difference between whether n is large or not. It's just not whether p is large enough compared to n.
I agree with you. You talk about another parameter, which is dimension of the input. I was talking about the number of parameters versus number of samples. All right. In this case, the 60 million versus the number sample. In our case, in computer vision, we are at the same situation as your situation. Our dimension X dimension is number of pixels. So you talk about millions. Each sample, you have millions of numbers. So same for deep learning mostly. And they in AlphaFold, they use the feature vectors, feature vector of a protein, for example. That's also pretty high actually. The molecular structure, binding structure, all those, that could be, but not as high as typically like an image or movie, that's very high. I agree with you. So that's why we cannot even, otherwise we cannot do anything, right? And you are hopeless. Right now we still have hope because dimensionality of the input is high. So that's why even we have one sample we can already estimate because the sample is the data. And that X was used to initialize our network weights in our method, DN3, our brain model. And the first input from the neuron input was immediately used to estimate the weight of the neuron, all right? Suppose we have 1,000 inputs, 1,000 dimensional inputs, and we 1,000 weights, and the input was immediately used to initialize my weights. So our weights is randomly initialized, but we start with initial random weights of the network before you take the first input. So the first input will immediately replace the random weights. So we proved that our random initial guess of the weights, which was used actually, is irrelevant to the outcome of the result. Because different initial weights only determine which neuron will end up learn, all right? And you lose in the luckiest network that the best fit, basically. You want to find the winner of network that learn the current input. And that's like competition. The best fitter will learn the current input. And the best fitter initially start with random initial guess of weights, but the learning rate is 1, retention rate is 0. So the first input will totally, immediately, 100% to replace the first neuron's weights. So we proved, because of that, our learning rate will change later on. We have optimality issue. The learning rate is automatically determined, coupled with the retention rate. So our network is always optimal in the sense of maximum likelihood, because our networks always compute the temporal average of the input. So temporal average of the input X and Z. In our case, both X and Z are used as input. So we have a top-down input, which is the muscle. Z is our muscle. Our brain not just look at what your input is in the eye, but also input in the muscle, because muscle is related to what you see in the eye. And if you are interested, you probably very useful for your area too, because that's the brain model. I repeat again, muscle, or what you speak, or X, what your muscle what you hear in the ear. What you hear in the ear is a hair cell, and your muscle, when you speak in the Z, they are highly important. That's one of the 20 million problems I talked about. And very few people understand it because they don't spend enough time on the neuroscience. And I got tremendous benefit from neuroscience. And that happened even early baby time or prenatal time. When the baby is in mother's womb and the muscle kicking of the leg, all right, or mouth slightly twisted a little bit, has a lot to do with what the eye see, all right, eye see. and the network is learning in a dynamic fashion from a single cell. And that's a little far away, but I just related to our discussion. So this is called a sensory motor. Sensory motor signals that the particular learning, D, then has this is the before testing. That was the last testing. That's the future testing. And the future testing is open. Last testing is available now. F is the time before. So it's very different from what you said. It's a batch data, then we probably get FVT. But in the developmental context, it's the time. The current time is the V, and what is called validation. And all the sample you learned the past is F, all right? And all the data arrive incrementally through one sample at a time, XZ, one sample at a time in the field. So it's a huge challenge in the learning because the sample learning incrementally, not in a batch like F. And deep learning in the field always use batch data. I said, don't, it's wrong. Because if you don't have the early F, you will not have Z. So VZ depends on the early F. So you cannot have the entire F and suppose you give all the Z. That's nonsense. And the learner must be autonomous. This is called active learner. The active learner must dynamically generate the muscle in order to learn continuously. All right. So this is another point I called sensory motor recurrence problem. And all the batch learning data are wasting so much humans data to label data. You cannot label the data. And our baby labeled the data himself using his own muscles. So our baby learner labeled the data on the fly. All right, so now we have FVT, right? Then what's our goal? Our goal is that this particular baby, all right, we cannot kill 1,000 baby and only keep one baby. We must say that every baby, regardless it's doing well in the class or not, what's his performance in the future for job, right? So we want to predict what's the coming out in outside our university, MSU. So that's what we need the expectation because this is random. In the absence of additional information, we want to test every 20 students, all right, give example here, and the worst one or best one in this particular test, and what's expectation in the future T. My position is that in the absence of additional information, the luckiest one on V and the worst one on V will perform on average. You say, no, and we have a CV, and I like your term, it's a CV. I said, no, we don't have CV. My position, we don't have CV, all right? You want to talk about CV, you talk about human. If it's a human, I agree, all right? And that's network. Network is greedy and only doing random fitting on F. So we don't have CV. I'm not sure I'll answer your question well.
I'm not sure. I mean, your example of like baby learning things, that's very nice. I mean, I'm not an expert like your learning. That sounds like doing predictions and using that in your future learning. There's a temporal order in your data, right? Okay, but again, I want to like take a step back and just come back to the easiest setting because that's where I have
sorry.
expertise.
I did not mean, but I like to give context in case that yes. In case that it's useful for your future work, because it might be useful, but just like it to this neural network or linear regression, support linear regression, from sample, then you do linear regression.
Yeah,
I draw a diagram that I'm not sure that diagram is useful, but I can So this is the diagram.
No, yeah, I was saying if we're just doing supervised learning with IID data, so there's no temporal order.
Yeah, agree.
And I wanted to train 20 neural networks on the fitting sets, and I picked the luckiest one on the validation set and the worst one on the validation set. And still, how can you say that the best one on the validation set is the same as the worst one on the validation set? I mean, we can say that we don't know for sure that the best one is going to be better than the worst one.
We don't know, right? We don't know.
We can say that we don't know for sure, but then you cannot say that they're going to be the same, because we probably have some confidence, or we have more confidence that the best one is going to be better than the worst one on the validation set, on the testing data set.
All right, good question. I was asking them the same question many times to me, and that's how I draw this diagram. Because I need to talk to my collaborators, and we are writing a paper to generate data. All right, to directly address your issue, because first you need the theory. Without theory, we'll not be able to really guide you to the experiment. So we did that. All right. So now in this diagram, this dimension x is the dimension of weights. All right, weights. This is a 60 million dimension. I call neural net plane. All right. I dropped the A. So you can consider A, the same thing. All right. Suppose I have a W and A. If W and A and put together maybe 1 trillion. All right. 1 trillion. All right. And this is the fitting area of a data set. I explained that one at a time. All right. So this is the place you start with the initial weights. Position A, position B, position D, position C. That's where you start the random weights. And I draw in one dimension D so they can visually see it. You can appreciate the problem we are talking about. Tremendously challenging. This is a 1 trillion. You talk about it 1D. Then this, you will like to have this one is the batch error. I don't do incremental error. Incremental errors just cannot be plotted clearly. I just plot the batch error. And then this is the fitting error. Fitting error is the dash line.
Can you remind me what is batch error? Because I don't know.
Batch error is the fitting set is get all the data in a batch available to the trainer in a single iteration.
Okay.
It's batch.
You're considering like stochastic grading, this and that kind of thing?
No, it's not stochastic grading. It's the availability of the data. Give example. Give example. Suppose I open my eye after the birth, I see the first image, but that image is not available now, right? My brain already took that image and using my muscle, crying muscle, already put in my brain. So that first image after my birth is not available. So I can assume that first image after birth is available. So human learning is not batch. You can only have the current input. You don't have all the old inputs.
Okay.
It's very tough. Brain is very, very tough issue.
So if I'm talking about IID data, then that's just...
If IID is still okay, but if the data arrive incrementally, then it's still IID. But if it's a batch, means that if I need 1,000 data points, and 1,000 data points is available to you for your predictor, then it's batch.
Oh, okay.
But if the data arrive one at a time, then you update your predictor. Then you have the second sample. Then you update your data, your predictor. Then you keep doing that. That's incremental.
Okay.
And brain is incremental.
Okay.
Not batch.
Okay.
All right. So now I say batch error because it's easier to see. All right. Assume that all the training data in F is available. So I can plot the curve. Otherwise, I cannot plot the curve. All right. Now, the dash line is fitting error on F. All right. We don't know all the points though. right? Because it's impossible. This is 1 trillion dimensional. We can only from the point that we have this network. In this case, we have 4 networks only. A, B, C, D. All right. I'm not talking about 20. In the Alex Grave case from Google, they have 20, but they probably train more than 20. But I at this point, I don't raise the point. All right. Many people train many times already. So assume that we have 4. All right. And then we only know where you started. We compute the fitting error and we compute gradient, all right, local gradient, all right. And the gradient method will go down the slope, all right, increase or decrease. That's for 1D. For 3D, you have to go along the gradient direction. It's against the gradient, actually. You want to minimize against the gradient. Then this red one, if we start from here, we go down to slope, So the red one will go down to this point. This point turned out to be the luckiest fit. But we never know. We never know that you start with here, you will end up with luckiest fit. So luckiest fit is too high dimensional, it's impractical. You agree? You only do locally, right?
Yeah,
locally,
right.
you look at fit, you compute the gradient only, and in this case, always increase, until the gradient magnitude is so small, then you stop.
Okay.
Right? It's called local pit. All right, it's a local minima. Then if we have the blue one will go end up here, right?
Yeah.
And the green one will go down because the gradient is reduced. You end up here, right?
Right.
So for the 3 balls, I call neural network ball, NM balls. NM ball will end up here. They're called the luckiest post. This is the luckiest post because the lowest one, and this one start with a really good place, but goes farther down. It's farther away. Farther away because you don't know. You don't know start with the best place D. You don't know, right? You end up with this one because you don't see the solid curve. Solid curves unknown test error. A solid curve the post validation error. This is the V. This is the V. This is the T test. And you don't know. Within training, you don't see that solid line. You don't see the green line either. During you only can locally see the dashed curve. All right. So you start at the best place for the validation, but you go the farther away. And the green one end up here, local pit, and the blue one end up with local pit here. But if you train all the vertical lines, the master post is this one. Right now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So out of 16 neural networks, this is the max post. Maximum error in the validation set. Post means the post selection after fitting. All right. And this is the luckiest fit among the 16. You know, this is the lowest fit, lowest local minima. All right. And then this is average post error. This is average. All right. So my position is that I'm not sure you agree with me. In the absence of additional information, additional modeling, that the luckiest post, which is here, all right, and this one, give example, or the max post, this one. All right, so look at this one, the luckiest post, and the max post. This is max post because this is the end over here. So the green is the luckiest fit, but the max post, right? The max post because this is the solid line. And then after this point, you want to see where they are in the green line. But you don't know the green line. The green line is like that. You know, what I draw is the range are similar and distribution more or less a uniform distribution. So you don't know. You don't know which point you are using on the green line to test that blue and the green ball.
Okay. Can I say something?
Yeah.
So, because you're just giving me like one example, like you probably just made this. I'm not sure whether it's real data or it's something
No,
made
not
up.
real data.
Real
Because you
data.
cannot
Okay, I
plot
see.
it. You cannot. So
Right,
I
right.
was trying to use a concrete example
Yeah.
to explain to the reviewer. First thing to explain to the reviewer. By the way, that it was probably the reviewer did not have time to read it very carefully. I have to really send that in the text, but he probably will not have time to really read it carefully. That's a problem. All right. So
Yeah.
even most reviewers don't have time to read the entire paper.
This is illustrative, right?
Yeah,
so
it's illustrative.
Yeah,
so
but
it's easier to see, right?
Yes,
So from
yes.
the green point, which is the max post, from blue point, which is luckiest post, you cannot say that this one or that one is positioned in the green line.
Right. You
Green line
don't
is,
know exactly.
You don't know.
Yes, you don't
And
know
the
exactly.
dimension is too high, right? And the number of samples we are talking about is much too few to have any uncertainty in the green performance. We don't.
Right. Without test data, we don't know anything about.
Yeah.
I mean, I should say we don't have a.
So we need to have a green line. We need to have a test,
yes.
right? But we
Yes.
don't. That's
Yes.
a cheating part.
And
That part is cheating.
but
the second is that we cannot hide those balls. We hide it. We don't report it. We don't report this one, right? We don't report this one. We don't report other ones. We only report this one. That's not fair. And this is not a test. It sounds like test. This is the first time this network sees this solid line. No. That's irrelevant because you are still picking.
Right. I mean, you're talking about things that we've already agreed on, and I'm just trying to talk about the point about like how do you compare the luckiest one and the least lucky one in the poster. No, I'm
very
saying
good question. Don't compare because there's no statistics information for you to compare. The only thing that all those points, green and the 16 point, all those twin, the expected error is average post. That's a probability. Average post is the average post.
No. The point of let me put it this way. This is one the plot you're showing is one particular example, and I mean I could come up with another example that looks like this.
All right, I think we agree with that. Right. Okay, so I will make another green line that goes like this.
What? So how do you know?
I will make the green line to be perfectly fitting the thin solid line. Maybe you can consider V as a T. But then I make up.
No.
I don't
know. I'm saying, for example, in the
with your curve.
In the valid. No,
with your curve.
For example, it's possible
you can be this curve. Maybe this curve existed, right?
Right. I mean,
sure.
then this
I like that. Okay, you have a good example. I didn't do that because I don't want to draw that way. And this curve you draw, maybe favor that C. Yeah. Okay.
Yeah.
But that's
in my favor the C, and D is the worst performing one on the
yeah.
But then on the other hand, the green curve might look very similar to this one.
No, I think green curve.
I'm not sure.
Look at the green curve, right? This green's curve, the worst becomes close to average. Do we see that? And
so why do you think
last one is also close to average.
Okay, why do you think in practice the green curve must be far from the blue curve in my plot? No,
in practice we never know because we cannot speculate, right?
I mean, on the other hand, we trained these networks on the fitting data sets, right? And the green curve, you evaluate the green curve on the independent validation set. And the blue curve is also an independent test data set. So they in some sense they should perform, and they should look kind of similar, those two curves.
All right, I get the point. I get the point. All right, this is not the first time. Many people are talking about. Right. So right now, your question is why the dashed line, solid line, and green lines, they don't fit.
They don't. They look so different.
They don't. They are not consistent, right? Right. And if you understand probability, then you don't ask. You don't even ask. Right. You should on my side. It's the probability. Otherwise, random.
They are random, but then they.
You are talking about they have a high correlation.
I'm just saying
you're talking about the F and the theta. It's F and the V and the T is not random among the parameter space. That's a baseless. It should be very high, very random. Because this is the parameter space. That's why you do fitting. Yeah, otherwise it don't fit in. Right? I'm talking about different fitting point. Do you see the error is so much different? Right? And if you agree
I see that they're different in your example. I should say.
You see that?
In your example,
if you agree, no, let me explain it. Okay, sure. Maybe you can see. If you agree my dashed line, you should agree my solid line. You should agree with my green line. Why? Because we have to train the network. And a different position, you end up with a different fitting curve. And unless you said that V and the F and the T are the same, then they totally congruent. They are totally congruent.
I know they're different, but they come from the same distribution. So So I kind of expect this one should be similar to this one, these two curves. So that's why that's why the superlearner works. The superlearner says you pick the best one here, and the best performing one should perform similar to the best candidate model in the test error.
All right, I'll repeat your question. This is a very important question. That's why we need to do interactively. You are saying that superlearner without testing will do very much the same as on the V, and I don't agree with that. That's our key difference.
Yeah.
And you already agreed it. You said we should have a test. And
yes.
And you said that T are very similar to V. I don't agree with that. T will be very different from V. That's what we understand probability. Otherwise,
I mean, it's an independent sample, but they're drawn from the same distribution. They have different realizations, but I mean, on average, they should look similar.
No, they're not.
If you fix the
depends on the given example the dimension. If dimension is very low,
yes,
right? The dimension is very low dimensional, and the range is very narrow. Given example, we have a handcrafted representation has only one parameter, like threshold. Given example, maybe what you said is true, but not 1 trillion dimensional space, not 60 million dimensional space. So your example maybe fitting what we call Gaussian method in least square fitting, because only one parameter, all right? And gradient descent and find the local minima, maybe one dimensional. Maybe even that case, it's not true actually, because that case does not have randomness. So gradient least square fitting, low dimensional, it doesn't have randomness. If you have randomness, like on the right side, there's error, right? The residual error, if you add even Gaussian noise, and what you said is not true. Just least square fitting, right? It's a classical least square fitting, and on the right side, you have additive noise. Then what you said is not true.
What?
IID, so linear model,
IID data.
yeah, plus
Yeah.
epsilon. The
Yeah.
epsilon is IID, all right? Y
Yes.
is 1 trillion dimensional space. Epsilon is IID. Not true.
What is 1 trillion? What,
Dimension of the Y or epsilon dimension is 1 trillion.
why? Wait, why is 1 trillion?
It's the let me see. It's a number of pixel, give them.
So this is the model you have. Y is
Yeah,
a
it's
linear
like Y typically in our case we already transfer from X to Y. Y is the class label. So
yeah,
X is 1 trillion pixels, give example.
okay, y x is high dimensional.
Yeah, 1 trillion pixels.
I don't know.
Yeah.
I don't know.
Then epsilon is the additive noise. 1 trillion.
Epsilon is
1 trillion noise in the image.
oh wait. I talking wait, what is the model?
Linear model as you draw, okay? Just linear model, beta naught plus beta 1 and X image plus epsilon, yeah. And the Y is the regression, right? It's the result.
Why is a real number?
Yeah, Y is the 1D. It's not 1D actually, but if you want the 1D, it's the regression output. Give example.
Yeah.
Could be error, right? Just but let me see. Typically, Y is a high dimensional. In our case, it's a number of class. It's in MNIST data 2000. 2000.
2000. Okay. Y is 2000.